So we spoke in general about different approaches to modeling the LOB. We said that there are a few classes of approaches that can be classified as economics-based single-agent models, statistical models, physics-motivated models, and machine learning approaches. It's needed for many different things, which may be estimation of different measures of intraday risk, for example, estimation of daily value at risk, or VAR. Another objective of modeling here is a very short-term prediction, about a second into the future, of price moves, which is used for designing of trading strategies. Yet another objective is an optimal trade execution that we already mentioned a few times before. So in this video, I would like to talk about statistical approaches. The main reference for this video is a paper by Ramaquand cited on this slide. In general terms, statistical models of the LOB incorporate two sorts of information. The first sort of information is the current state of the LOB. And the second piece of information are various statistics of the order flow. For example, arrival rates of market and limit orders. And as we just said before, different types of approaches can be used to this end. They can vary from purely statistical to machine learning to physics-based models. But most of them share many features in common. Most of them view arrivals of different types of orders, such as buy, sell, limit, and cancel orders probabilistically. And those probabilities per unit time are called arrival intensities. The other thing these models should include are execution of market trades via priority rules. And all this produces model predicted price dynamics that can be compared with the data. This still leaves lots of freedom regarding how exactly this should be done. And one approach that can be called a microscopic approach would be to model all price levels simultaneously. Another possible approach would be to focus instead on explicit modeling of only the best prices on both sides. In other words, this approach is more phenomenological, as it focuses on the part of the LOB where the trade actually takes place. And characteristics of other price levels in the LOB are used here as a source of different features, if we use here the language of machine learning. There are also some interesting physics-based approaches of this sort. And for example, you can see papers by Don Farmer, Jean-Philippe Bouchou, and their co-workers on these topics that I already mentioned. So one possible approach is to model the LOB as a multi-level queuing system. Remember that we talked about priority rules in price and in time. They implement the FIFO, or first in, first out principle of a queue. So a simplest idea for modeling an LOB as multi-level queue would be to first break this into independent queues. And if we assume that for each price level, arrival rates for different orders are mutually independent, we can build simple and tractable models. For example, we can use Poisson processes to describe arrival of events, such as limit or market orders. This produces simple models because for Poisson processes, durations between consecutive events are independent and distributed exponentially. So in this picture, events of crossing the spread would appear as Poisson events. Their intensity would depend on the state and statistics of the LOB, And assuming stationarity after deseasoning this data, we can estimate these intensities as parametric functions. And all this will produce simple and tractable analytical model. So far so good, except that these models would be too simplistic. In reality, the main assumption of Poisson processes is strongly violated in data for this case. As we just said, the key assumption of all models that use Poisson distribution is that inter-event durations there are independent. But in reality, arrivals tend to cluster in time. And in this graph, you see changes in the size of the ASKU for the Citigroup stock on June 26 in 2006 in Rama-Kohn paper, 2008. Each order or cancellation is a data point. If the value is positive, it's a limit order, and if the value is negative, it's a market order or cancellation. And the frequent large spikes and oscillating amplitude that you can see here are all signs of clustering in time. Therefore, the standard Poisson modeling is not adequate here. A big question, of course, is what causes this clustering. And one school of thought believes that such clustering can have endogenous origin. This means that it would not be driven by some sort of external signals, but rather by some internal dynamics. And there are many very interesting questions that can be addressed if you have limit order book data. One very interesting topic is the problem of market impact. We already talked about market impact and mentioned the classical work on this topic by Bertsimes and Law and Almgren and Chris. We also talked about how these ideas can be taken to reinforcement learning in the last week of our course on reinforcement learning. Now, these classical papers deal with price impact of actual trades, that is, of market orders. But there are tons of different specification of market impact models in the literature, and there are many different definitions of what exactly the market impact is. There are, for example, permanent versus transient impacts, linear versus non-linear models, and so on. And some of these approaches seem not to be quite consistent. And this was noted by Rogers and Singh in their paper from 2006 on liquidity modeling. They remarked that the notion of permanent impact of an individual trade is somewhat problematic because if there is an individual permanent impact, then other trades should also have permanent impact. But if this is true, then it's not clear what is modeled in such approaches in the first place. But this is just a side remark, and the point I wanted to highlight here is rather different. The point is that price impact in these classical models is modeled as a function of trades, that is, a function of market orders. But as we already know, a vast majority of events in a limit order book are limit orders and cancellations. And the rate of cancelled orders often reaches 90 or even 95%. Therefore, if we simply discard these events, we might lose some important information. Now, another paper by Kont and co-workers drew attention to the importance of limit order book events for price impact. So they showed that price changes are sensitive to a measure of order flow imbalance. And this measure is given by the difference between the limit orders minus market orders and minus cancellations, and divided by the depth of the price level. So once we identify this metric as a driver of price changes, we can, for example, formulate a simple Langevin type dynamics for such system. For the lack of time and space, we will not go into details of this and some other very interesting statistical and physics-based models of the LOB. But I recommend you looking into these papers on their own, including papers by econophysicists, Bouchou, Farmers, and others, if you want to dig deeper into this topic.